Alrighty, welcome to the AP Stats review session for the Unit 7 makeup test. Here's our first review problem, and it's a problem in which the true proportion P is 0.35. So we have P is 0.35, and suppose that 35% of students at a particular academy have type B blood. And suppose that the population size, capital N, is 1,100. So there's 1,100 students. We're going to select 92 students for our sample. Now, by the way, is this sample size too big or too small? Take a moment to check the 10% condition and the success-failure condition. So check three conditions here to see if our sample size is okay. 10%, success, and failure. So 10% condition, what you should be checking here is 10 times 92 has got to be less than 1,100. 10 times 92 is 920, and since 920 is less than 1,100, we're okay on the 10% condition. N times P, what did you get when you took 92 times 0.35?
32.2.
Okay, so it's 32.2, which is greater than 10, so we're okay on the success condition. And then let's take 92 times 0.65, and what did you get for that?
59.8.
59. So here's how you would actually show it. You'd say, okay, 10% condition, check. NP greater than 10, check. NQ greater than 10. 58.5 is greater than 10. Okay, so we have permission to proceed. What we're going to do now in this example is, so is a normal model appropriate? Yeah, so if suppose the question for part A was, and you'll probably end up wanting to take a picture of this. So let's get the question up there. Is a normal model appropriate? Question mark. Well, to answer that question, we have to check the 10% condition, success, and failure condition. So the answer is yes, and say, yes because of that. So the next question is, part B, is what is the probability that we observe X greater than or equal to 39 type B students? Now, what do you think the definition of this random variable X is?
Number of students with type B.
Close. We're going to actually be using, well, see, this is a binomial situation that can be approximated with a normal model if we want to, but it's binomial. And so when you said that the definition of X is the number of students that have type B blood, that's close. Since it's a binomial model that we're going to be using, you would have to say out of 1,100.
Okay.
So the definition of X, in fact, let's write a let X statement up here. Let X equal the number of students out of 1,100 that are type B.
Is it 1,100 or 92?
No, it's, oh yeah, you're right. It's not out of 1,100, it's out of 92. Good call. Yeah, I made a mistake on that. Out of 92 that are type B. Okay, so that's what X is. And if you're going to use a binomial model here, you have to define X, then you're going to have to write a probability statement, but you're also going to have to specify the model. So would you please tell me what would be the two parameters on this binomial model that we're going to use to answer this question? So you're gonna have to pick. That's not B for type B, that's B for binomial model. Okay, so I'm seeing National Public. It has to be 92. Because there's 92, that's the most we could possibly get, and National Public, the probability of success is 0.35. Now, one thing that you should probably know is that when we ask the question, what's the probability that we observe 39 or more students with type B blood, that's technically a conditional probability. Even though it's not written out, what it means is that what's the probability that we observe X is greater than or equal to 39, given that the true proportion is 0.35. And I want you to write this on the board with an eyeball around this, because this is what we're going to observe, and the brain symbol around this, because that is what we believe. And it explains really why it is we're doing this probability problem. We are interested in knowing really whether there's sufficient evidence to believe what the authority figures are telling us. That's why we're interested in this probability in the first place. We're thinking that this is just a hypothesis. We're going to say, well, they're telling us it's 35% of people are type B. I wonder if that's really true. We're going to do a study with 92 randomly selected students, and we're going to find out, well, how many of our students are really type B? So anyway, this is what it really means. However, this is how it will be written on the test. Or this is what you can get away with at this point. This is what you can get away with. So here's a challenge for you. What I want you to do is, using the binomial model, write down 3 of the triplets that give you the probability of X is greater than or equal to 39. There's going to have to be a ... in there, because in the binomial model, there's 92 plus 1, there's 93 numbers in the model, and you need all of the, there's 93 triplets. There's 93 triplets, and you need the triplet for X equals 39, the triplet for X equals 40, all the way up to the triplet for X equals 92. So I'd like you to take some time now to write out those 3 triplets, including a plus ... I'm going to pause the camera while you work on that. Okay, so we gave you some time to work on that. Now, the concept here is that there are up to 92. So there's 93 columns of numbers in here. And if we were to take the time to write out all 93 columns, you would see a column for X equals 0, X equals 1, X equals 39, 40, and then all the way up to 92. So we want 39, 40, all the way up to 92. So the X equals 39 triplet will be 92 choose 39.35, 39.65 to the, what is 92 minus 39? Have you done that already?
It's 53.
53, okay. The second triplet would be plus 92 choose 40.35 to the 40, 0.65 to the, these are going down, so it would be 52, plus ... and then the last triplet, the third triplet you have to write would be 92 choose 92.35 to the 92.65 to the 0. Now what I want you to do is write the calculator notation that you would use to find the value of this probability. I'm going to press pause. If you're watching this at home, press pause. Well, that didn't quite show up on the camera. Okay, so let me put that up a little bit higher so you can see it. Those are the 3 triplets for the probability that X is greater than or equal to 39. Now write some calculator notation that would get that most efficiently into your calculator. Okay, so now the calculator notation using National Public Radio, which is designed to give you the left portion of the probability distribution. Well, we want the right portion. We want from X equals 39 all the way to the right. So to get from 39 all the way to 92, we're going to take 1 minus everything from 0 up to 38. So we're going to stop at 38. That's the thinking. So instead of going from 39 to 92, we're going to take 1 minus binom CDF of national 92, public 0.35, Corradio's K sub R. And the last number on the right of the interval is 38. So type that into your calculator. And yeah, that it's crucial that you know how to get that triplet of numbers using national, public, Corradio. So type that in. I'm going to pause while you type. Okay, so when you type that in, you got 8.5%. Now let's interpret that, 8.5%. So remember what the big picture is. The reason we're doing this is because we want to know whether or not we should believe the authorities when they say that 35% of students have type B. So based on your probability of 8.5%, what would you say, yes or no? Is it really reasonable to believe that 35% of students have type B blood? Talk to me. Yes or no, and why?
Yes, because it's above 0.05.
Yeah, that's it. The answer is yes. In fact, let's write that down for part C. Part C, the question is, based on your answer from part B, is it reasonable to believe that 35% of students have type B blood? There's type B and then there's problem B. So part C, write down the question so you can take a picture of this. Based on part B, is it reasonable to believe that what the authority said is true? That 0.35, 35% of students have type B blood. So Chad's reasoning was that he said yes because 8.5% is greater than 5%, which means our observation is likely. Based on the assumption of the null hypothesis, the assumption is that the authority figures are telling the truth. And let me just put this in perspective. Let's compare this to what would happen in a situation, and yeah, so you can start watching the video at the 13-minute mark. You missed the first 13 minutes, so you can watch the rest. And wait, oh, there's something blocking the view of my camera. That's weird. Oh, I see, yeah. Yeah, the holder was blocking the view. So let's contrast this with the situation of what this could have been. Because you need to understand how scientists think and what scientists like and what scientists don't like. What if we had been doing a study and the probability that we observed x greater than or equal to 39 given the probability is equal to, and this will be a different sample size, so I won't give you all the details, but what if this had come out to be 0.00038? What if the answer to the probability problem had been something minuscule like this? Well, really, what we're doing is we're saying, well, we made this observation. We had 39 students who had type B blood, on the assumption that it's really 35% that have type B blood. Scientists do not like believing in things that lead to probability calculations of observations that are really, really unlikely. If they end up saying, well, I'm supposed to believe that 35%, if the probability that what I actually observed, given that belief, is really, really low. I don't like believing in things that lead to low probabilities. So I'm going to reject that belief, I'm going to reject that hypothesis, and I'm going to conclude that I have sufficient evidence. In this observation, I have sufficient evidence that P is not equal to 0.35. That's how scientists think. They use probabilities to guide what they believe. Now, if you're the sort of person who's not willing to let numbers dictate what you believe, then you might not want to become a scientist. You might want to find another truth source. But science is coming up with the drugs that cure the diseases. So I don't know what you're going to believe in. I mean, science came from the Bible, so you can either believe in science or believe in the Bible that produced science, or just find something else to believe in. Let's go on to the next problem. So if you want to take a picture, now's the time to take a picture of that. Problem 2. We're going to have 2 random variables in problem 2. And, they say you can't compare apples and oranges. Actually, if you know their standard deviations, then you can compare apples and oranges, because then we can figure out, is this orange of this weight? If we know the mean and the standard deviation, we can say, well, what's the probability that we randomly select an apple of this weight and an orange of that weight? And based on the z-scores, whichever one has the bigger z-score is the one that's more unusual. You can compare apples and oranges. Now let's do something else with apples and oranges. Let's say that we're going to let X represent the weight of a randomly selected apple, so of an apple. We're going to let Y represent the weight of an orange. It's a random variable because when you pick an orange at random, it's going to have a mean and standard deviation. It turns out that X is distributed normally. So the distribution of apple weights is normal with a mean of 40 ounces and a standard deviation of 3.1 ounces. It turns out that the weights of oranges are also normally distributed with a weight of 34 ounces, they're lighter, and a standard deviation of 2.8 ounces. Now, what we want to do in part A, this is question 2, part A, based on all this given information. What is the expected difference in weight, and what's the standard deviation? So, what is the expected difference in weight between a randomly selected apple and a randomly selected orange? Well, first of all, what model are you going to use? I see people at the sideboard using X minus Y as their model, which is the correct model for the difference in weight. So would you please take a moment to find the expected value of X minus Y and standard deviation of X minus Y? Feel free to use a calculator. I'm going to pause while you make your calculations. Okay, so we're back. You probably got basically 40 minus 34. You have to show your work. You have to be expected value of X minus expected value of Y. So you got 6. And then when you did not plus or minus, but the square root of 3.1 squared variances, and by variance, in fact, I remember someone was talking to, I said variance and they wrote down variance. They spelled it like this, and I realized, oh, we're not communicating, because the correct spelling of variance in statistics is V-A-R-I-A-N-C-E. Variance is standard deviation squared. So we take the sum of the variances add even when we're subtracting. So when you did the square root of 3.1 squared plus 2.8 squared on your calculator, it looks like you all came out with 4.177. These are ounces. These have to have labels. So if you had 4.177 ounces, you're in good shape. Now part B. Question B. Suppose, okay, we want to find out what is the probability that, let's see, I want to think about whether we're going to pick a certain number of, or no, we're just going to take, okay, what is the probability that a randomly selected apple weighs 4 or more ounces more than a randomly selected orange? So in fact, you know what, write down the words, because I want you to study the words. What's the probability that an apple weighs 4 or more ounces more, so the word more is in there twice, 4 or more ounces more than an orange. And just to give you a hint, you're going to have to use the results from part A to go model, mechanics, and conclusion in part B. So I'm going to pause the camera while you are working this out. Have at it. All right, so we're going to take a look at what Garrett did. He said that probability, he set up his model with 6 in the middle. He shaded from the right on 4. The z-score was negative 0.479, and normal CDF gave him 68.4%. Yep, that's what we're expecting because it was more than 50%. And just a quick, if you can hold this camera right here, I want to write something. Now, it is nice to be able to take this expression and write it using variables. So essentially what we're saying is, what's the probability that x minus y is greater than or equal to 4? And x minus y. Or we could even say, what's the probability that the difference is greater than or equal to 4? And we could define the difference as x minus y. So then if we were to put a title, and this is one place where I think people can improve in their understanding of statistics, is that these models will be more understandable to you if they have a title. And the title could be, d equals x minus y. Here's a normal distribution of the difference between the weight of the apple and the orange. So difference on average is 6. We want to know when is the difference greater than or equal to 4. So you could define d as x minus y and then get a nice clean algebraic expression of what the probability is in the first place. So, all right, we're going to go down to a part C on this, and I'm just going to pause the camera while I show